Okay, so in this video I'm going to be talking about heaps and I'm really going to be talking about Huffman codes and why we need to use heaps and a priority queue and all that stuff. Like the whole purpose of this is just to tie all this into Huffman codes. So first of all, we're going to learn about heaps. We're going to go in the order, but let's read about heaps. So it says it provides O of 1 access to the maximal element. So that's for a max heap. We could also say that if it's a min heap, it'll provide O of 1 access to the minimal element. And what that just means is that the smallest one is on top in a min heap, or the largest one's on top in a max heap. So we can always take the top one off. We already know where it is, so we can immediately get it. And then also supports insert and delete in O of log n time, because we're going to be treating this heap sort of like a tree, a binary tree, which is full, and that means that we can do insert and delete in O of log n time, which is a property of trees. So let's read the definition. A max heap is a binary tree which is full in that each level is full except for maybe the last, which is filled from the left. So this is what the tree looks like. We just keep filling it down. It's like we're reading a book, sort of. And it's like lines in a book, and then the end of a line doesn't have to end perfectly, but we always start from the left, and we're moving this way. So this is going to satisfy the heap property. So remember, we're talking about a max heap, so that the top element is the biggest one. So that's for this case. So this says for all nodes n is greater than n left, and n is greater than n right. So say here's n right at the top. Then the left is small, or n is bigger than this one, and n is bigger than this one. Now we don't actually care about which one of these two, the left or the right, is bigger. That's not what it says. All it cares about is that the one above it is bigger than the two below it. So the largest value will always be at the root. You should try to make sense of this yourself. If the one above is always bigger than the two below, then in order for this entire thing to hold that property, the top one has to be the biggest one. So make sure you can understand why that is, and try to draw a picture of it if you can. Okay, so thanks to property 1, we can easily represent this with an array. So we're going to see how we can represent this with an array. So right here we have this array, and we've labeled all these numbers like this, which makes sense because, well, okay. So this is sort of like why we have these numbers here is sort of going to be tying into the Huffman codes, which maybe I can get into right now since we're talking about Huffman codes. So if you notice right here, this is the top is a 1, and then right over here, this one is 1, 0, and so on the left is 1, 0, and on the right is 1, 1. So what this means is if I'm at this top one right here, 1, and I'm going to the right, I'll append a 0 to my number. So I have a 1, and if I go this way, I append a 0 to the number. And you can see that if I have this 1, 0, and I go right, I append another 0 to the number. So basically what that means is going to the left will append a 0, and going to the right will append a 1. So you could sort of see how that would be. Now that was sort of like a digression from the whole concept of heaps, but I think that's why these numbers are what they are. But also we could see this actually has a property of a min heap, in that the smallest number is the one on the top, and it's smaller than the two beneath it. So you see the 10 is smaller than 100 and 101, the 11 is smaller than 110 and 111, and of course the 1 is smaller than 10 and 11. So you could see that this has a property of a min heap. Now, because first of all, a tree is not a real thing in a computer, it's just a way for us to see something in our mind, we could be representing it any way we like. So for us, we can actually represent this entire tree in an array, and the array allows us to put the tree back together because we know we have like a system for figuring out which node goes into which index. So right here, like for instance, the top node, we can label all these nodes like if you just go in order. Say we label this top one 1, and then we go 1, 2, 3, 4, 5, 6, 7. So just in order like we're reading a book, then this 1 will go here, This 2 will go here. This 3, which is 11, will go there. 4, which is 100, will go there. 5, which is 101, will go here. 6, which is 110, will go there. And 7, which is 111, will go there. So we see that we're able to just basically, in order, put these nodes into an array. So there actually is a way of organizing this using a couple of formulas. So it says for any I which is between 1 and n, the index of the left I is going to be 2i, and the index of the right I is going to be 2i plus 1. So let's just actually confirm this. So this one at the top, we're going to call this index 1. So we're indexing by 1 at the front. So if it's C++, we would have to change it just a tiny bit, but it's really not that big of a deal. So say this is 1, then the index to the left of the left is 2 times 1. So this is 1, so this is 2 times 1, so this is 2. Is this going to index 2? Yes. The right of 1 is 2 times 1, which is 2, plus 1, which is 3. So to the right of 1 is 11. Is 11 in third one? Let's see. 1, 2, 3. Yep, the 11 goes there. Now let's just look at these 11, see if that works, because it's going to get a little bit more confusing. So 11 is 3, right? So to the left is going to be 2 times 3, which is 6. And to the right is going to be 2 times 3 plus 1, which is 7. So let's see, it's 110 and 6, and 111 and 7. Let's see, 1, 2, 3, 4, 5, 6. See, 110 isn't 6, and 111 isn't 7. So we actually can see that this works pretty much for the whole thing. It seems like it's going to work. So now we're going to see how to insert and remove some building blocks. Okay. So we know that the only possible violation is that left I is greater than I or right I is greater than I. So first of all, let's try to recap. Let's try to understand what type of a heap they want. So this looks like we would want to make a max heap, right? So this one we want to make a max heap. So if left I is greater than I or right I is greater than I, then that means that it's not a max heap, because the max heap says that I is greater than left I and I is greater than right I. So this top one has to be bigger than this one and bigger than this one. And we're going to see if it's a violation. So the way we're going to do this is pretty simple. Like, first we're going to talk about it, and then we're going to look at the code. So what we're going to do is we're going to do it one step at a time. We're just going to compare 3 elements at a time, right? So this is a mini heap, right? This is just, these 3 could be considered their own little heap. So 10 is the one on the top, and we want to make sure that of these 3, the largest one is going to the top, right? Because say we see, oh, 11 is bigger than 10, we know 11 should be switched with 10, but then 11 is not bigger than 13. So of these 3, we need the 13 to be on the top, because 13 is going to be bigger than 10 and 11. So this is what we're going to do. We're going to switch 10 with 13 first, right? So then you see we take 10 and 13, we switch them. So now we have 10, 13, 11, 12, 9, 4, 8, right? So then once we've switched with one of them, we're going to take the one that was switched, and then we're going to treat this as a heap and make sure that this is fixed. Okay? So we're going to see, okay, we have 10, 12, and 9. We know that 12 is the largest, so we have to switch 12 with 10. And once we've gotten to the end of this, that means we're done. We don't have to fix it anymore. Now, I just want to say something, because maybe that you won't notice this, or maybe you'll be confused about this. If, for instance, this 11 right here was out of place, if there's any issues with this 11, right? Say there was a 15 right here instead of, because this 11 you can see is bigger than 4 and 8, so it's fine. But if there was a 15 here and this was out of order, fixing this 10 would not fix that. So even though we would fix the part with the 10, we would not actually fix this part. So I just want to be clear, because when we want to fix it, we have to fix the whole thing. And well, I'm getting too much into it, but basically, what this procedure is called Heapify down, which means that we work from an element on the top and we just keep working it down until we get to the bottom. So you see we had 10 and we kept looking down until we were to the end. Now this Heapify down, one call to it does not fix the whole tree. We might have to do it several times in order to fix the whole tree, just to be clear. So so we're going to look at Heapify down, and let's just see what this is. We're going to see what these parameters that are being passed, and we can see if we can make sense of it. Okay. And I would encourage you to make your own heap and sort of play around with it and see if you could understand how this would work with this. So we're passing right here an integer pointer, right? So that's going to be like an array, where it's like we're passing an array into a function, and because it's a pointer to the array, we're going to actually be able to manipulate the actual array, not just a copy of it. And then the size tn, I'm just going to guess that n would be maybe the number of the size of the array, or let's just say like the size of the array. So the size of the heap, so maybe for this n would be 11, or no, sorry, not 11, 7. So say n would be 7. And then we're going to say size ti is going to be the heap one we're working with. So we started with 10, right? So 10, the I of 10 is 1 in this case. Because remember, this is pseudocode. This is not C++. So the index starts at 1. So if you want the index to start at 0, you're going to have to manipulate it just a little bit. But I think you could try to do that yourself. So it says if 2i is greater than n, return. So if which that means is that this doesn't have a child, right? So let's see right here. This one, let's just look. This is 1, 2, 3, 4, right? So this is 4. So if I is 4 for this one, 2i is going to be 8. Now I is 7 because that's the size of the tree, or n is 7. So if this is bigger, there's not going to be a node beneath it, so therefore it's going to be a leaf. So that means we're done. Once we get to a leaf, we're done. We don't have to heapify down more than the leaf. So we're going to say that the max child, so if this doesn't return, that means that it has leaves, right? So we're going to say the max child is 2i, so we're going to say the max child is the left. Then we're going to check if 2i plus 1 is less than n, so this has to also be true, less than or equal to n, and h of 2i plus 1 is greater than h of max child. So let's just go back to this example that we're talking about. So first of all, remember, so we're talking about 10, right? So 2i, let me just zoom out a little bit. So I is 1, so 2i is 2, right? So 13 right now is the max child. So then we're going to see if 2i plus 1 is less than n. So this is 3, 2i plus 1 is 3, is less than 7, yes. And h of 2i plus 1. So h of 3, so remember, our third index is going to be 11, right? So 11 is greater than h max child. So max child is 13. Is 11 greater than 13? No, it's not. So the max child stays 2i, right? So the max child stays the index, which has 13. Okay, so now he says if h of I, right? So h of I is 1, so if 10 is less than h of max child. So 10 is less than 13. Yes, 10 is less than 13. Then we're going to swap 10 with 13, right? So then we swap 10 and 13. And then once we've swapped 10 and 13, we call heapify down. Like I said, remember, once we swap the 10, we're going to heapify down where the max child was. So the max child was a 2. So you see the 10, it went to where the 2 is. And then we're going to heapify this down. We're going to make sure we fix this. And we see pass h again. We pass the same array. And we pass n, which is the number of the size of the array. So it's still 7. And then we pass max child, which is 2. So we're going to doing the same thing too. And then the return statement is going to make sure that once we get to the end, we're finished. So that's what the heapify down thing does. And the heapify down is going to be good when we're putting things into, like if we're inserting things into our heap, right? Like if we insert something at the top, then we're going to, or it doesn't matter how we insert it. Like I think we'll get to that in a second. Actually, like before I talk too much, like if you think about it, we could insert one thing and it could break it. So we want to make sure that we heapify it. But again, we'll get more into this because I have to look at these notes too. So so let's consider the opposite case, right? Okay, so we're going to consider the opposite case, right? Because before we cared about if the parent was smaller than the child, and that was what we cared about, the parent. But now we're going to care if the child is greater than the parent. So it's the same thing, but it's just we're caring about the child first instead of the parent. And we'll see in a second how this works. So let's just see. So let's consider the opposite case. Say a leaf node I might be bigger than the parent. So So we're going to call Heapify up, right? So we pass the same exact parameters. We're going to be passing the child, or we're going to be passing the children. And like our exit condition is that if I is equal to 1, we're going to be done, right? So like once we've gotten to the top, which is 1, we're done with this this function, right? Which is going to be recursive probably. So if h of I divided by 2 is less than h of 1, right? So let's just understand what does that mean exactly. So say right here, like let's just look at this 14 for a second, right? This 14 is 7, right? Remember, it's at index 7. So this is at 7. And if we take 7 divided by 2, remember it's an integer. So 7 divided by 2 is 3.5, which is integer is 3. So let's see, 1, 2, 3. So we're seeing if this 6 is less than this 14, which it is, right? So we want to swap them because we want the bigger number to be on top because this is a max heap. So we swap them, right? And then we call Heapify up right at this index, right? So now we have the 14 here, and we want to check and see if it's bigger than the 10. And it turns out the 14 is bigger than 10, so it calls it again. And then we're at 3, so then when we call I divided by 2, that's going to give us 1, and then it's going to be returned. So it's going to pretty much just kind of like travel up the side until it's done. So you could see that like this kind of would be more like inserting. Like this might go good with inserting something into the array, because like if you add something to the end of the array, then you kind of have to fix the Heapify up. And the thing before, the Heapify down might be good for removing. Say we remove the top one, which we're gonna be needing for the Huffman. Like for the Huffman, there's a reason why we care about this top one and why we care about for a Huffman. So we're gonna see in a second why this all makes sense. So how to use Heapify down up to insert and delete. So you see right here, insert and delete. So we have insert. So we're going to pass in the array. We're going to pass in the size of the array by reference, because we actually want to change the actual size of the actual array. We don't want to change a copy of the size. We actually need to change the actual size. And then we want to insert x, right? So this x is what we want to put in. So if the size is 7, we want to insert x. We need to make it bigger, right? We need to make it size 8. So we take n, 7 plus plus, so now n becomes 8, and it becomes inside the real n. And we put that index 8, we put x in there, right? So once we put x in there, that is when we want to Heapify up and make sure that the x is placed properly and the thing is still a heap afterwards. So definitely do a practice with that. Even maybe take this one right here, and try to insert a new number into there, maybe a bigger number, and see if the Heapify up thing works, because I think it will work. So that'd be a good practice for you. And then in extract max. Okay, so we're going to want to extract the max, and I think for Huffman, I think we're going to be talking about the min. I'm not 100% sure, but I'm pretty sure we are. But again, we'll get into that in a second. I gotta look at the notes. So to extract the max, what we're going to do is we're going to swap. Okay, so this is just a comment. But what we're going to do is we're going to be swapping the biggest one with we're going to swap the first one with the last one. So let's just see what we're doing. Let's just take a step back and see what we're doing. So we do n minus minus, so we're making the size smaller. Remember, we're passing the size by reference, so we're actually changing the size. So, because if we're taking one of them off, we obviously need to make the size smaller. And then Heapify down, we're going to be calling, okay, so you can see what's going to happen. So Heapify down, we're going to just be, let's see, what are we doing? N minus minus Heapify down n1. So I gotta go take another look at what the Heapify down does. H, n, and 1. So Heapify down, we're going to be dealing with this top one, and we're going to have to make sure that the top one is the right size. So let's see why this swap is. I think this shouldn't be a comment. Okay, let's pretend this is not a comment, okay? We actually swap the, okay, so this is not a comment. Never mind. Okay, this is not a comment. We're going to swap the the last one with the top one, okay? So let's just look at this one for a second, right? So this is 14. So we're going to swap this 14 with this 6, right? So we're going to put the 6 there and put the 14 there, right? So obviously the 6 is not going to be in the right spot for this type of heap, but the 14 is going to be the end, and that's okay for what we're doing, because once we put it at the end, so say right here the size is 7, right? We're going to swap the 6 and the 14, and then we're going to say that the size is now 6 n minus minus. So the size is 6, right? But it still exists in the memory, but it's just like we don't think it's part of the heap anymore. So we call Heapify down with 6 now, because n is now 6, and 1, which is the top one, and we just bring it down. We just fix it down. So we're going to take the 6, and we're going to switch it with the 10, and so on, like that. Now, we're going to return h of n plus 1, right? So n is 6, n plus 1 is 7. So because the 14 is still there in the memory, we're going to be able to get that number, and we're going to have the value that we want it to. So we're going to be able to take out the maximum value from the heap, okay? So then applications, priority queue sorting, this is like a less stupid version of selection sort. It says write an O of an algorithm to build a heap from an unordered array. Okay, so I don't think I want to get into this right now. Let me see. I guess I should go into the Huffman codes. Okay. So I guess this video is going to be really long, but okay, let's just see. That's just what it's going to be. So, problem. So let's see. Given a set of symbols S1 through Sn, each with frequencies F1 through Fn, find a set of code words for the Si which minimizes the expected cost, i.e. length of a communication. So sort by 1 over F1 ascending, then just iterate. Alright, so let me just sort of give you an idea of what this means first of all. So a set of symbols, say we're talking about letter. We're reading a document, with letters. And we have like 15 letters, so we have some A's, some B's, some C's, and some D's. Say we had like 5 A's and 3 B's and 4 C's and 3 D's or something like that. So the S would be A, right? S1 is A, and then F1 would be 5. S2 would be B, and then F2 would be 3, and so on and so forth, just like that, right? So we see that A5 means that it's more common than B, which only has 3. So A is more common than B in this case, right? So there could be any case you want. Anyhow, that's just how to relate S1 with symbols, right? So we minimize the expected cost of length of communication, right? Because we know, say we use A way more than we use B, we're going to want to make the way that we transfer the A, say in a binary code, we want it to be a shorter code because we know we're using it all the time, so we want to keep it shorter since it's going to take up more of our space. So it says strawman. Okay, so I don't know what that means, but we want to sort by ascending, right? So the bigger the frequency, so A had 5, then we want to sort by 1 over 5. So bigger frequency means that it's going to be the beginning, because the bigger the frequency, the smaller this fraction, and then we want to sort it in ascending order like that. So So then just to go talk about some binary, right? This is what this is saying. Si, say we could represent it as 1. So say we're just going to be representing every integer or every symbol as a binary number. So we're just going to go in order. Let S, the first symbol be 1, the second symbol be 1, 0, the third symbol be 1, 1, and so on. So the problem with this, and the reason why we have to figure out a better way of doing this, is say we get 2 1s next to each other. How do we know whether we said it was two S1s right next to each other, or it's S3. There's no way to tell if we're looking at this huge file of just binary numbers. There's no way as to tell which one of these it's supposed to mean. So therefore, we need to figure out a better way. So it says use a binary tree to only store valid symbols in leaf nodes, right? So I think I was talking a little bit about this before, but we could make the top one 1, and then if we go to the right, and the top one doesn't have to be 1. We can make it 0. It doesn't matter. We have to just choose one of them. So what we could say is if we go to the right, or sorry, we go to the left, we append a 0. And if we go to the right, we append a 1. So therefore, we're going to have 1, 0, and 1, 1. So, but the thing is, like the whole concept of this is that we only want to store symbols in leaf nodes because a leaf node can never be a prefix to another leaf node, right? Because if this is 1, 0, 0 and this is 1, 0, 1, you wouldn't, like this 1, 0 is a prefix to 1, 0, 1 and 1, 0, 0, but that's not going to be a symbol we're going to store. So you could sort of, I think it's pretty obvious that having these as leaf nodes is not going to allow one thing to be a prefix of another, and therefore if you look at a whole bunch of binary numbers right next to each other, you could actually figure out exactly what each symbol is supposed to be represented as. So it says, how do we minimize expected costs? So I mean, this just says like for a certain cost, we let's see, code word for SI. C has the code word for SI. So if there's less code words, okay, so this is what it means. So the more frequently we see a letter, say we see a lot of A's, right? So A, the frequency is bigger. We want the code word to be shorter, right? So, and if the frequency is shorter, we'll let the code word be a little bit longer. So we want to minimize this. So that's the best way of doing it. So this is Huffman's method. Not sure what this says. Let's say create nodes like this, SW. Let's see, insert them into priority queue. Okay, so we're going to insert them into a priority queue, high priority equals low value. So initially create nodes and insert them into a priority queue. Okay. Give me 1 second. The loop the following process, extract the 2 highest priority lowest weight nodes. Okay, so we're going to figure out first of all which are going to be the lowest weight and which are going to be the highest weight, right? So say there's 5 A's, right? And then we also had 4 C's, right? And we had 3 B's and we had 3 D's. So write this down because I can't write anything right now. So the 2 highest priority nodes are going to be A and C, or actually we could just sort of maybe go with SW. Okay. This is probably going to be harder for me to explain without drawing it, but I'll try my best. So let's see, what is this? You know what? I'm gonna start this video in a second. Let me just look at this notes. All right.